Hi guys, see you speaking again. In the previous videos we focused a lot on the digits and on the decoders. Today we are going to focus much longer on the counters. The purpose is to build a two-digit counter and to build it successfully, meaning doing at the same time the troubleshooting. So let's find out how the things are gonna go. Here we have a canvas and we're going to fill it with information. Here in the bottom are going to be the counters. And then when we finish with the counters, yes, we can connect decoders and digits. But let's start with the counters. The one I chose are some of my favorite circuits. You can have either 74-193, regardless the flavor, LS, H, whatever you have, or 40-193. This is the TTL version, this is the CMOS version. And the numbers here are the same. This is a binary counter, a 4-bit binary counter. The name is a bit more complicated. It's a 4-bit synchronous up and down binary counter. But at this moment, we just know it's a binary, it's 4 bits. And let's see what are the terminals we have to connect first. Of course, if I'm going to put here the VCC, and here the ground, the purpose is going to be, again, to build a two-digit counter. So I'm going to do the same on the other package. So the VCC and the ground. So here is going to be the plus 5 volts. So far, so good. Now, once you put the power supply, so that's a standard package, then we have to understand what are the most important terminals for the control. This is going to be something similar, and this is why it's one of my favorites, is because counting up and down is going to be pretty similar to the volume of your phone. I have a button to go up with the volume, and I have a button to go down with the volume. It's going to be pretty similar on our counter. So to count up or down, we're going to have two terminals. But in the way they are organized, these ones, they are organized like this. So they need a falling edge. This is why there is a bubble here at the input. And they are called clock inputs. Clock inputs, we put a little triangle inside the package to signal that. So this is to count up, and this is to count down. Very easy. Here we're going to bring a signal from our push button 1, here to count down, push button 2, and I won't insist on these ones. They are just giving a falling edge taken from our micro trainer we built a couple of weeks ago. So here, what do I have to know? I need a falling edge here or a falling edge here. Obviously, you cannot count up and down at the same time, so you have to pick which of them you want to count. Very good. So once we have this, the next thing we have to figure is where I'm going to collect my results. I'm going to collect my results over here. I'm going to have my 4 outputs. Exactly like for the flip-flops, my outputs are going to have the notation Q, and they're going to be D, C, B, A. Remember, when counting, here is the least significant bit, and here is the most significant. This is why I start the signals from the right side to the left. And we're going to do similar here. We're going to have 2 control terminals on the right of the package. This is to count up, this is to count down. And here we're going to have the 4 outputs of the second package. Absolutely similar way. D, C, B, and A. So then, here we are going to collect the results. However, there is something we have to do for our troubleshooting at least. So we are going to monitor the result of the outputs on some LEDs. So here I'm going to connect the LEDs together with their limiting resistors. So the limiting resistors connected to the ground. And here are going to be our connections. LEDs are going to be connected over here. So I'm taking my time to draw the diagram because I want everybody to understand. These are 4 LEDs, one for each output. So we're gonna go like this. Now we make the connections. Straightforward. So this is how we monitor our outputs. All the resistors here are going to be everything you have to 20 ohms to about 500 ohms. They're going to be perfect. I'm going to do the same here. So here I'm going to put the limiting resistors. There are going to be 4 of them because we have 4 outputs. And here I'm going to put my diodes, my LEDs. Okay, and exactly as we did on the other side, we're going to make connections over here. And then this is how we monitor our outputs. So again, we have for each of the counters, we have 2 pins to control. They are called clock inputs, counting up or counting down. We have the 4 outputs. We have the 2 terminals for the power supply. We need 2 more things. One more control terminal, I'm going to put it over here, is connected to plus 5 volt. I won't discuss about this terminal today. I'm going to discuss it when we pass to applications of these counters. But at least I'm going to tell you this is called load. And if you just want to count, it has to be connected to plus 5. So plus 5 volt load. Okay, it's plus 5 volt because I want to keep it up because it has a bubble. And one last terminal for the control is going to be a reset terminal. So reset RST, reset RST. So if you need to cancel the operation for whatever reason, here it is. I'm gonna draw a line up to here. So these are coming from the push button 3. And the reset, as you can see, has no bubble on the package. Who established that? The designer of the package. So we just have to follow what the designer did. So for this one, you need to pick up from the push button a rising edge. This is what it needs to reset. If you don't apply the rising edge, so the signal stays low, the package is not reset. Okay? Very good. So now we know what to do with this. One last thing before we follow the wiring, we have to put some pin numbers here. For the VCC and ground is very easy. The package is supplied with 16 terminals. So 16 and 8. These are 5 and 4. And these are 7, 6, 2, and 3. Load is 11. Reset is 14. We do the same on the other one. So 5 and 4. 16 and 8. 7, 6, 2, and 3. The reset is 14. And the load is 11. So far, so good. So now we have our counters. I'm going to put the same code here. 74,193 or 40,193. With the 4 LEDs on one of them and 4 LEDs on the other, now we have both of them ready. Now there are 3 things you have to follow in order for the troubleshooting to be successful. The first thing you have to watch is anytime you put the power supply on, you have to watch the consumption. If it ever looks something like that, 1 amp or even more, like here it shows 3 amps, you stop the power immediately because it means you have a short circuit somewhere in your circuitry. The second thing you have to follow is that you make these connections to the LEDs, because this way you can see exactly what's going to happen to the 4 outputs of each counter. And the third thing you have to follow, because you need first to do the troubleshooting, at the beginning, both counters are going to count similar way. The meaning is, whatever is coming here from the push button 1, you are going to supply the same signal over here. Whatever is coming from the push button 2, you are going to supply the same signal over here. So this way, both counters should do exactly the same job. Just watch. I put the power on. And now, if I press the button, the green one, my counter should be able to count up. I reset it first. So this is the push button 3, push button 1, push button 2. The diagram here is taken from the micro trainer, so I don't need to insist on that. What I need is on the counting up, I need the signals to stay up if I don't push anything. So when I press the button, I'm going to give a falling edge. So if I'm connecting it right here, a multimeter on the pin 5, okay, on the pin 5, and we're going to watch the multimeter. We're going to watch the multimeter over here. As soon as I press the green button, watch the multimeter. It goes to 0. I release it, it goes back to 1 logic. So the signal stays up, and when I press it, it goes down. Okay? So now, I reset it again, and I count. When I press the green, the red lights should be in the same position for each of the counters. So because my bar graph here has 10 LEDs, the 2 in the middle, I keep them green, because it's a bicolor bar graph. And I'm going to only count on the red. So this is 1, this is 2, this is 3, this is 4, this is 5, 6, 7, 8. Remember the binary, 1000 is 8, 1001 is 9. Then I have 10, 11, 12, 13, 14, 15. So when all the red LEDs are on, I have the biggest possible number, 15. And if I press it one more time, it's going to go to 0. But if I count backwards, it goes back to 15, 14, 13, 12, 11, 10, and so on, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So my counter is able to count up, this is 4, or down, 3, 2, 1, and so on. And I can reset it with the push button 3 every time, okay? So both counters are doing exactly the same job. Now, when I make sure they do both the same job, then I can focus on the next stage of the diagram, which is what? Keeping the signals coming in the same way on both counters. I'm going to connect the 2 decoders and the 2 digits. So I'm starting from the top with the digits, because the type of the digits, they determine the type of the decoder. So as you can see here, this is a MAN 6780, which is a common cathode display, and I chose the ones which are very user-friendly. You're going to see very soon why. They have both 2 terminals for the common. So common cathode. I'm going to put the same here. Common cathode. This is why they are connected to the ground both. And then, because they are common cathode, I have to pick up my decoder to be a common cathode one. So let's pick up the 7448. 7448. So this one does what? It does the conversion between the binary and the 7 segments of my display. So this black box represents the 7-segment display. So this is why I put its symbol here to know. Now let's start with the decoder. It has 4 inputs, and the inputs are going to wear the same letters as the outputs of my counter. This is going to be D, C, B, and A. Somewhere here, I'm going to have the VCC, and obviously it needs a ground connection. The ground. The same thing for the other one. It needs a ground and it needs a VCC. Here are the DCBA, the 4 inputs. Then there are 3 terminals I don't want to talk about. I just mentioned them last time we talked about the decoders. Some control terminals. You're going to find in a lot of manuals that these 3 terminals, if you leave them floating into the air, they should be considered by the internal diagram of the decoder as being one logic. But to make sure it does this, better just to connect them to +5. So this way we're going to be sure they respect the position because they have a bubble. And then I'm going to have 1, 2, 3, 4, 5, 6, 7 pins for my segments. For each of the digits, I'm going to have 7. On the decoder, these are going to be the outputs A, B, C, D, E, F, and G. Similarly, I'm going to have the same for my digits. And on the other side as well, A, B, C, D, E, F, and G. A, B, C, D, E, F, and G. So the only remaining thing here is to put some pin numbers before we make the connections. So 6217, 6217. Don't forget, I gave you the pin numbers of all these things in the previous videos. Like, if you take a look, there is a reminder over here for different kind of decoders. So don't worry, I know them by heart, but if you have any doubt, you have them right here. This is 7448, okay? So then I'm going to complete the numbers. These are 3, 4, and 5. The control terminals I don't want to talk about, okay? And then what's remaining, the pin numbers for the power supply, 16 and 8. That's very easy, 16 and 8. And then for the 7 segments, you're going to have 13, 12, 11, 10, 9, 15, and 14. Okay, same thing here, 13, 12, 11, 10, 9, 15, and 14. As for the 7-segment displays, 3 and 8 are the common terminals. You don't need to connect both physically. You need one of them at least to be connected. And then the order is 7, 6, 4, 2, 1, 9, and 10. And the same for the other, 7, 6, 4, 2, 1, 9, and 10. This is for what kind of digit? Is for MAN 6780. So not be wrong about this. 6780, okay? Because this is the common cathode. So now, in the moment you completed all this, what do we have to do? I'm going to connect my 7448. I'm stopping the power. Don't make connections with power on. So let me just have them connected. one here, one on the other side, over here. Okay, and now the 2 digits. One is going to be right here, and the other one in the similar position over here. Okay, let me just make sure it's in the right spot. Okay, something like that, okay? So in the moment we put the power on, we reset. They should both go to 0. Now, if the situation is respected like we counted before with the counter and the LEDs were right, you should see exactly the equivalent of the binary number 1 over here. Then the equivalent of the binary 2 over here, and so on. So this is just counting up, and the other one is counting down. Now what may happen, and this is the next step for the troubleshooting, when you make these connections, decoders and digits, there is a lot of wiring. So can you do mistakes? Of course you can. I did all these mistakes during the years, okay? First thing that may happen is this. So as you can see here, you try to count, the binary is working fine, 3, 4, 5, but only one of the digits is working. What happens then? Don't suspect the digit is defective. Probably you forgot to connect the ground for the pins 3 or 8. So when you connect the ground back, like I'm doing now, everything goes back in order. Another mistake you may do, which is a typical one, I'm just going to simulate here a trouble. Let me do this. Apparently, everything goes fine. Just watch. I'm keeping counting. Now, for the 1, everything was fine. But when you reach the number 2, something wrong happens here. What actually happened was I just had 2 wires reversed, let's say accidentally, for the segments over here, which are F and G. And if I just put them back in the right order, everything should go back like it was before. So you were able to count properly. So this is the advantage. This is the advantage when you have, I'm going to do this again, when you have 2 digits, because both of them are supposed to do the same job. You see the numbers, they seem to be the same. Even here, they look the same. 9 is the same. But here is not the same anymore. So this is supposed to be the equivalent of 10. Because remember, with 1 digit, you cannot expose the number 10 in hexadecimal. Then 11, 12, 13, 14, 15 is blank, and then 1, 0. But here the problem is the fact that you reversed accidentally 2 wires, it makes some numbers appearing properly and some others not. And because of this, since you have both digits wired, you take one of them as reference so you can fix the other. So that's the key about having the 2 digits receiving the same signal at the same time. Because if any of them goes wrong, you can fix the other, okay? So now everything goes back in order. Whatever the symbols are, remember the symbols are referring to the sheet we have for the 7448. So for the 10 we have that symbol, 11, 12, 13, 14, 15. So our displays are following exactly the shapes. And then if you want to count backwards, everything is fine. But then, since you have all these understood and you can do the troubleshooting right now because you know how it's going, I'm telling you what is another reason this is one of my favorite circuits. And I'm talking about the counters. is because right now, the counters we're talking about, they are just keeping counting in binary. But obviously, there are some applications needing binary. There are some others, though, when you only need them to count in decimal. Because you cannot expose, like, say, the gas pump, these kind of numbers in hexadecimal, nobody will understand. So then, instead of having this package, what am I going to do? This is a fully binary package, which is counting in hexadecimal 0000 up to 1111. And I don't want this to happen anymore. But then I'm going to have another package I'm going to connect right here, which is exactly the same pinout of that one, 193, but it's called 74-192, or the equivalent one in the CMOS, 40-192, 192. And it's going to work exactly the same like the binary one, absolutely the same pinout, excepting is a BCD counter. So this is a BCD. In other words, it's stopping at 9. It won't be able to give you combinations bigger than 9. So I'm going to mark it here too, 74-192 or 40-192. And this is a BCD. And take a look what I'm going to do. I'm simply stopping the power and then extracting the two counters one by one. I put this one away and I put instead the BCD counter, which is the 192. So as you can see, I don't modify anything about the wiring, absolutely nothing, okay? I just want to make sure it's in the right position. I'm going to do the same about the binary one on the other side. So this is why you need to leave some room between the packages, because just in case you have to be able to extract them, to take them out, either because you have a doubt about the functioning, or like in that situation, I'm just replacing them with another number. And the only thing I'm doing is what? Power on. It doesn't matter the scrambled symbols I see at the beginning, because at this moment I have no means to give an automatic reset. It's going to be for another project. But I just press the reset. The reset means both of them, they go in 0. As you can see here, all the LEDs are off because it's 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. Exactly like the others. But now instead of going in hexadecimal, they go back to 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. See? So these are BCD counters. And now there is one more thing remaining. We did the troubleshooting for these ones. We can find out that both are working identical way. But the purpose of the project for today was to have both counters working one following the other. In other words, counting from 00 to 99. And now is going to be the last step we do. Take a look what we do. Initially, we had this red line coming from the pin 5 to the 5 of the other one, and pin 4 to the 4. So both of them are counting up or down at the same time. We break this line anywhere here. So only the counter on the right side, the least significant digit, only this one receives signals from the push button 1 and 2. And we are going to discover that this package has more terminals. I'm describing 2 more terminals today. Here is one of them, and here is the second. And this is called the carry output. This is called the borrow output. And what do? The carry output is used when you count up. And anytime you count the full cycle and it reaches the 9, because for the BCD counter we have right now, the biggest signal is 9, and it goes back to 0, it delivers right here a falling edge. This one, the borrow output, when you count down and you count 9, 8, 7, and so on, 1, 0, when you push the button next time to go back from 0 to 9, it gives another falling edge right here. So if you connect now the carry output to the counting up of the next counter, so remember, the red wire is cut already. You cannot have signals coming from two directions at the same time. And you connect the borrow output to the pin 4, which is counting down. Now, this one, when finishing a cycle, should just increment the next one to do the job. Take a look how we do. These are the two wires, exactly like the two buttons here. There is a green wire and a red one. Coming from here, from the two buttons, green and red, and both counters were related like that, receiving signals at the same time on the same pin 5 and pin 4. Now I reconnect the pin 5 on 12. The pin 4, I remove the wire and I put it on 13. Right here. I reset, you see? And now I count. 0, 1, 2, 3. You see now? Only the least significant counter is working right now. The other one is still at 0. Waiting for what? Waiting for a whole cycle like now. From 0 to 9 there was a full cycle, and when I press it one more time, it's going to be incremented this one. So this is how we count 10, 11, 12, 13, and so on, and it goes to 20. If I go reverse way, of course it can. See? And if I go back, below 0 is what? 99. And so on, it goes back 89, and so on. So I can count up, or I can count down. What did I do for that? I just cut the red signals because I only use them for troubleshooting to make sure both channels, both counters were doing the same job, okay? And now after I check all that, I remove the wire from here and I connect it where? I connect this pin 5 to the pin 12 of the previous counter. This is exactly what I did here. The green wire here is the pin 5 of the second counter, but is connected to the pin 12 of the previous. And the pin 4 of the second counter is connected to the pin 13 of the previous one. And this is why this is working fine. Because now the counters are cascaded. They are working together. Each cycle done on the first counter is going to trigger the next counter to do the job. Okay? We do this one more time. We can reset anytime we want, and we can count. See? And it's going to be incremented the second counter anytime you reach a full cycle on the first. This is how the counters can be connected together. And we've done at the same time the troubleshooting. So this way it's very difficult to go wrong because you can watch the channels at the same time doing the job, and only at the very end, only then you cascade the counters, so you make the connections between the two counters to count together from 0 to 99. That being said, thank you very much for today. We're going to see each other next time. Bye-bye.